Hey everyone, welcome back for another deep dive. Today, we're going to be looking at some really cool stuff in AI. Um, Specifically, three technical methods for compressing these large language models, or LLMs as they're called.
Yeah, these LLMs are everywhere now.
That's right, and we've got some fascinating research to dig into today. We'll be looking at pruning, quantization, and knowledge distillation.
It's amazing how these techniques can really boost AI performance and even help address some real-world problems like cost and accessibility.
Yeah, it's pretty mind-blowing when you think about it.
Absolutely. And what's really exciting is that these techniques are not just theoretical ideas. They're actually being used right now to optimize AI.
That's awesome. So let's start with the why. Why is compressing these large language models so important in the first place?
Well, as you can imagine, these models are very resource intensive. They require a ton of computing power, memory, and powerful hardware to run.
Yeah, it's like trying to run the latest video game on an old computer with barely any RAM.
Haha, exactly. That's a great analogy. And it really highlights the issue. Not everyone has access to a supercomputer, and many real-time applications need AI to be fast and efficient.
Yeah, if you're using AI for something like threat detection, you need it to work quickly.
Precisely. Or think about those personalized experiences on your smartphone. A slow AI just isn't going to cut it in those situations.
Right. So by compressing these models, we can make AI more accessible and run it on less powerful devices, even opening it up to a wider range of applications.
Exactly. Plus, it's not just about performance, but also about sustainability. Compressing these models can lead to significant savings in energy consumption.
Okay, so we've talked about the why. Now let's dive into the how. First up, we have model pruning. I think of it like trimming a tree. You remove the unnecessary branches to make it healthier and more efficient.
Yeah, that's a good way to visualize it. Model pruning is essentially identifying and removing those parameters or weights in a neural network that have minimal impact on the model's output.
Okay, so how do you know which parts to prune without messing up the model's performance?
Right, so there are different algorithms and techniques for that. One common approach is magnitude-based pruning, where you simply remove the weights with the smallest absolute values.
So basically the ones that aren't contributing much.
Yeah, the idea is that these weights don't contribute much to the model's overall computations, and by removing them, you can simplify the model without sacrificing too much accuracy.
Got it. Are there any interesting findings from research on pruning that have really surprised you?
Absolutely. Research from Data Nexus on unstructured global pruning has been quite fascinating. They applied this technique to a variety of models, including DeepLab v3, MobileNet v3, UNet 50, YOLO-X large, and different YOLO-8 variants.
Whoa, that's a mouthful. And what were the results? Did it work?
What's remarkable is that even after pruning 90% of the models, some of them still performed really well.
90%. That's wild. It seems almost impossible.
I know, right? It really highlights the potential of pruning to drastically reduce model size without a huge impact on accuracy.
Okay, so we've pruned away the excess, and now our model is leaner and meaner. What's next?
Next up, we have quantization. Imagine switching from a high-resolution image to a slightly lower resolution one. The picture's still there, but the file size is way smaller.
Okay, so less data, less memory needed. How does this work with AI models?
So with quantization, we reduce the precision of the numbers representing model parameters and computations. Instead of using 32-bit floating point numbers, we can switch to smaller 8-bit integers.
So by using smaller numbers, you're basically making the model more efficient. But I'm guessing this could affect the accuracy.
It can, but there are ways to minimize that. One common approach is to use a calibration dataset to fine-tune the quantization process.
So you're tweaking it to make sure it still works well.
Exactly. And if the initial accuracy loss is too high, we can also use something called quantization-aware training. This means the model is trained specifically to adapt to lower precision from the start.
Clever. It sounds like finding the right balance is key here. What are some of the benefits you typically see when applying quantization to LLMs?
Well, depending on the model and the specific quantization scheme, you can see up to a 4x reduction in memory footprint, along with much faster inference speeds.
Wow, that's impressive. Okay, so we've covered pruning and quantization. What's the last technique on our list today?
The last one is knowledge distillation. Think of it like a teacher-student relationship where a smaller student model learns from a larger, more complex teacher model.
So the student is soaking up all the knowledge from the expert. I like it. But how does this transfer of knowledge actually happen?
So it's not just about the student mimicking the final output of the teacher model. It's about learning the entire reasoning process. We use something called soft targets from the teacher model to guide the student.
Okay, and what are soft targets exactly? How are they different from just giving the student the correct answers?
Instead of just giving the final answer, the teacher model also shares its intermediate predictions, the steps along the way. These soft targets provide a much deeper understanding of the problem. The student doesn't just learn what to predict, but also why.
Ah, so it's like learning the concepts behind a formula, not just memorizing the formula itself. That makes a lot of sense.
Precisely. And one of the biggest advantages of knowledge distillation is that it allows us to create much smaller models that can run on devices with limited resources.
That's amazing. So you can have a powerful AI running on something as small as a smartphone.
Exactly. And despite being smaller, these student models can often achieve accuracy comparable to their larger teacher models. This is a game changer for real-time applications where speed is critical.
Wow, I'm already seeing how these techniques are going to revolutionize the way we develop and use AI.
Absolutely. It's a truly exciting time to be working in this field. Welcome back. So, last time we started exploring these techniques, model pruning, quantization, and knowledge distillation. And now let's dig a bit deeper into some of the technical aspects.
Yeah, let's get into the nitty-gritty. We talked about pruning those unnecessary parameters. I'd love to hear more about the different ways you can actually do that.
Sure, so there are two main types of pruning, structured and unstructured. Think of unstructured pruning like going in and just zeroing out individual weights in the model.
Okay, so very precise, like
Yeah.
a surgeon.
Yeah. It's a pretty straightforward approach, often a good starting point for compressing models. But if we want to get those really big gains in efficiency, we might need to think bigger, consider the model's architecture itself.
Interesting. And that's where structured pruning comes in.
Exactly. With structured pruning, you're focusing on removing entire structures within the model, like maybe whole neurons or even entire layers.
Wow, that sounds intense.
Yeah.
What are the trade-offs between the two approaches?
Well, unstructured pruning is generally easier to implement. It doesn't require changing the model's architecture. However, the benefits might be limited compared to structured pruning, which can give you much bigger reductions in size and complexity.
Makes sense. So it's like choosing the right tool for the job.
Exactly. And within pruning, you also have local and global scopes. It's another important distinction.
Oh, right. You mentioned that before. What's the difference between them?
So with local pruning, you're focusing on specific areas within a layer, while global pruning looks at the whole model when deciding what to prune.
I see. So global pruning has a broader view, while local pruning is more targeted.
Yeah, you could say that. It's all about finding the right balance, being effective, while also making sure you don't remove anything essential.
Pruning is starting to make a lot more sense now. Let's move on to quantization. You talked about using smaller numbers to represent the model's parameters. How does that actually work in practice?
Okay, so think about how we represent numbers. 32-bit floating point numbers are super precise, but they take up a lot of space. Quantization is like saying, hey, let's try using 8-bit integers instead.
So it's like compressing a file. You're sacrificing a bit of quality for a much smaller size.
Exactly. And that reduction in precision makes a huge difference. Memory usage goes down, computations speed up, and you end up with a much more efficient AI.
But how do you make sure that reducing the precision doesn't ruin the model's accuracy?
That's where the calibration process comes in. We basically fine-tune the quantization process to minimize accuracy loss.
You're making adjustments to ensure it still works well.
Right. And if the accuracy loss is still too high, we can use something called quantization-aware training. This means the model is trained from the beginning to handle this lower precision.
So it's like teaching it to be more efficient with less information. Are there different ways to do quantization?
Yeah, there are. Post-training quantization is done after the model is already trained, which is easier. But quantization-aware training, while more complex, often leads to better accuracy overall.
Got it. It's a trade-off between simplicity and performance.
Right. Okay, that brings us to knowledge distillation, the last technique we talked about.
Yeah, this one was really interesting. The teacher-student analogy, where a smaller model learns from a larger, more experienced one. How exactly does that knowledge transfer work?
So it's not just about the student getting the right answers, it's about understanding how the teacher got there. We use this special loss function called distillation loss. It measures how closely the student's predictions match not only the correct answers, but also the teacher's predictions.
So the student is learning from both the right answers and the teacher's insights. That's cool.
Yeah, and this training on what we call soft targets, which are the teacher's predictions, allows the student to really gain a deeper understanding.
It's like instead of just memorizing facts, they're learning how to think.
Exactly. So what are some advantages of using knowledge distillation for compressing these LLMs?
Well, one big one is that we can create much smaller models that can run on devices with limited resources, like phones and stuff.
It's amazing to think that these powerful AI models could soon be running on everyday devices.
I know, right? And despite being smaller, these student models can often achieve similar accuracy to their larger teachers.
This feels like a major breakthrough in AI. It's like we're opening up a whole new world of possibilities.
It is, and knowledge distillation has even wider applications. We can create specialized student models for different tasks. We can adapt large models to new domains, even enhance the performance of open source models.
Wow, this is really incredible. It seems like we're on the cusp of a new era of AI accessibility and efficiency.
We are. And there's still so much more to explore. In the last part of our deep dive, we'll look at some real-world applications of these techniques and talk about their potential impact on the future of AI. Welcome back to the show, everyone. It's been an awesome journey exploring the world of LLM compression. I'm really blown away by all this.
Yeah, it's amazing how far this field has come.
It really is. So we've covered pruning, quantization, and knowledge distillation. But I'm wondering, with all these different options, how do you actually choose the right technique for a specific task?
That's a great question. And it's important to remember that there's no one-size-fits-all solution when it comes to LLM compression.
So you have to consider the specific needs of each model.
Right. Each technique has its strengths and weaknesses, and the best choice really depends on the specific challenges you're facing and what you're trying to achieve. What's the end goal?
Okay, so it's all about context. Can you give us some examples? Like, when would you choose one technique over another?
Sure. Let's say you have a model that's really limited by memory bandwidth. It's struggling to handle the data. In that case, quantization would probably be your best bet.
Makes sense. Reduce the memory footprint so the model can run more smoothly.
Exactly. But what if the bottleneck is computational complexity? What if the model is just too slow?
Then pruning would be the way to go.
Yeah, exactly. By removing those less important parts, you can really streamline the computational process.
So pruning tackles the processing side, while quantization addresses memory constraints. Okay, that makes sense. Now, what about knowledge distillation? When would you use that?
Well, knowledge distillation is really useful when you need to adapt a large, complex model to a specific task. Or maybe you need to run it in a resource-constrained environment.
So like on a device with limited power.
Right. By transferring knowledge from that big teacher model to a smaller student model, you can create these specialized, lightweight versions that can run on pretty much anything.
It's amazing to think that we could soon have powerful AI running on all kinds of devices, not just supercomputers.
Absolutely. And as these techniques continue to evolve, we're going to see even more sophisticated approaches to LLM compression.
So what's the big takeaway here? What should our listeners remember about LLM compression?
Well, I think the most important thing to remember is that it's not just about optimizing AI performance. It's about making AI more sustainable, more accessible, and more useful in the real world.
It's about making sure that everyone can benefit from the power of AI, regardless of their resources.
Exactly. And as these techniques continue to develop, the possibilities are truly endless.
Well said. It's been a fascinating journey exploring all of this with you. Thanks so much for being on the show.
Thanks for having me. It's been a pleasure.
And to our listeners, thanks for joining us for another deep dive. We hope you enjoyed the show. Until next time, keep exploring and stay curious.